Good morning to all of you. I am Dr. Alok Agrawal, and this is your 13th lecture of course Internal Combustion Engine having code ME501. So in last class we have studied what is the difference between air standard cycle and real cycle. Okay, and with that discussion we came out with that there are three main factors on the basis of which we can differentiate the air standard cycle or ideal cycle with the real cycle or actual cycle. So in this class, we will discuss those three factors which are the main factors which distinguish between the air standard cycle and real cycle. So the three factors that we have seen are time loss factor, direct heat losses, and exhaust blowdown losses. So in today's class, we will discuss all these three factors in detail. So first, to start with time loss factor. So in this figure, you are seeing that it can be seen that 1, 2, 3, 4, and 1 denotes our standard Otto cycle, which is also called air standard cycle. Okay. So now we will see that how the factor that is time depend and it will change the shape of the cycle or the behavior of the engine. So start with time loss factor. So, in a standard cycle, we have seen that heat addition is assumed to be instantaneous process, whereas in actual cycle, it is not an instantaneous process. It takes some time. It requires some time, and that time is a definite period through which the process of combustion will be accomplished. So, in this diagram, if we'll say that in air standard cycle, 2 to 3, this is our constant volume heat addition, as in case of Otto cycle. Here, the piston is at top dead center, and it is assumed that the heat addition process is instantaneous process where the volume is constant. But actually, it is not the case. Okay. In actual, what happened here? The crank doesn't move anywhere. It is at certain position, and because of that, the piston is at top dead center. Okay. But in actual cycle, what is happening? Crank rotates around 30 to 40 degree during the process of combustion. Okay, so it is not an instantaneous process. It takes some time, and that time is converted into the revolution or rotation of crank angle, which is come out to be 30 to 40 degree. Okay, so this 30 to 40 degree is a time duration where first the ignition start or initiation of a spark to the end of combustion. And because of this, because in actual cycle that the combustion is a progressive combustion, it is not instantaneous combustion, there are certain losses, and that loss is called loss because of time loss factor. Okay, now there will be a loss during this period, and it is called time loss factor that I have already seen. Due to the finite time of combustion, now we are seeing that the combustion requires some finite time. It is not a instantaneous process. So in case of ideal cycle, what is happening? The peak pressure, where we are getting the peak pressure, it is at point 0.3, okay, which is around 50, in between 50 to 60 bar it is seen. But because of finite time of combustion, that peak pressure is will not get this peak pressure when the volume is minimum. What does it mean? It means that when the piston is stopped at center, in actual ideal cycle, we consider that the maximum pressure take place when the volume is minimum. But as we have seen that the crank is continuously rotating, and hence the piston will continuously moving, so we'll not get peak pressure at minimum volume, but we get peak pressure. Here it is given that point C when the piston it starts moving away from top dead center and approaching toward bottom dead center. So we are getting the peak pressure at point C in actual cycle, not in point 3, which is the case of ideal air standard cycle. Okay, so this is, and because of this it has been seen that because of this what is happening, there will be a area under the curve will be reduced, and as the area under the curve reduced, the work output reduce, and this reduction in work output is because of time loss factor. Okay, so the pressure therefore rises in the first part. Here again we have seen that when the piston started moving from top dead center to bottom dead center, what is the pressure when the piston is at top dead center? It is B, at point B. Now it has been seen that at the first part of the working stroke or power stroke, when piston start moving from top dead center to bottom dead center, the pressure is increasing. So we are getting pressure rise in first part of the working stroke, that is from point B to point C. So here the ideal cycle and actual cycle distinguish from each other. Now this point represents the state of gases had the combustion been instantaneous and an individual additional amount of work equal to the shaded area shown hedged would have been done. What this point is saying? This point is saying that if the process is instantaneous, if the combustion process is instantaneous, we will get this much extra amount of work, which is shown by this hedged area. Okay, so there is a loss of work which reduces the efficiency, and it is called burning time loss, and this come under the category of time loss factor. So in this point we have seen that because of progressive combustion instead of instantaneous combustion, we are getting less work in a cycle. And it is obvious that instantaneous combustion is not possible. It is ideal and it is not possible at all, because combustion requires some time that we will see in our unit 2. So it will require some time. It can't be an instantaneous process. Okay, so because of this there will be a reduction in work and work output and efficiency. Okay, now coming on to the second factor, that is direct heat loss factor. During combustion, what we are seeing, what we are doing, that in case of Walt timing diagram also we have seen that uh, okay, during combustion process and expansion stroke, we have seen that heat flow from cylinder gases through the cylinder wall, because of combustion there will be a large amount of heat produces. Okay, so it has to be rejected uh, time to time, so that there will be a controlled temperature maintained inside the combustion chamber. So we use water jackets or cooling fins depending upon our engine. Okay, so it is sure that during the expansion stroke, because of combustion, during the combustion process or expansion stroke, there will be a heat will flow from inside the combustion chamber to the outside via some cooling medium. Okay, some heat also enters piston head and flows through the piston ring into the cylinder wall or is carried away by the engine oil. So there are some losses of heat which is happening. First is through cooling medium, second is through lubrication. Okay, this heat loss during combustion will naturally have the maximum effect. And this heat loss, which is at the starting of the power stroke or expansion stroke, this has the maximum effect, while the heat loss just before the end of expansion stroke. Means when the expansion stroke is about to end, at that time, whatever heat is getting lost, it has the minimum effect on the overall output of the engine. But actually, what is happening? When the power stroke, at the beginning of the power stroke, whatever amount of the heat is rejected, it is having maximum effect, because that heat can be converted into work. Okay, but the heat lost during the end of the compression, sorry, expansion stroke, it has very little effect, because tendency of that heat to be converted into work are minimum. Okay, so it has been seen that heat lost at the beginning of the power stroke has maximum effect, and the heat loss at the end of expansion stroke has very little effect. Suppose if we are recovered the complete heat loss, then what we will say, it is experimental data, that when we, if we are able to take the recover the complete total heat loss, we can make our work output 20% more. Okay, so 20% of the work we will get more if we can able to extract or recover the complete amount of heat that is getting lost due to cooling medium or lubrication. Now the effect of heat loss during combustion is to reduce maximum temperature. Whenever the heat loss occur in combustion, what is the effect of it? Heat loss. It will reduce the maximum temperature, and because of that, specific heat will reduce. Because as we have already seen that specific heat is a function of temperature. So what is happening? Specific heat will reduce as the temperature reduce. And how temperature is reducing? It is because that heat is carried away by the cooling medium or lubrication medium. So whenever the heat will loss, there will be decrease in temperature, and with the decrease in temperature, specific heat will reduce. And once the specific heat will reduce, what will happen? See, when the specific heat will reduce, what happen? The amount of heat required to burn the fuel will reduce. To raise the temperature of fuel by 1 degree centigrade, it will reduce. So there will be a more complete combustion. The combustion will be complete when there will be a reduction in temperature. Specific heat will reduce, and there will be a complete combustion, which increases the efficiency of the cycle. So if we'll overall we will analyze the direct heat loss, we can say that because of this heat loss, there will be a reduction in work output, but there will be a increase in efficiency. So so there will be optimization instead. So it has been seen that it is better that some amount of work will go through heat so that we will get maximum efficiency, and will though the work output will be reduced, but we will get maximum or improved efficiency. If we'll not let the work go out in form of heat, then what will happen? Though our work output will increase, but the efficiency of the cycle will reduce, because we will not able to get complete combustion, and some amount of fuel will go unburned from the combustion chamber, and that will also have one effect, that it will increase the pollution. Okay. Now the last one, that is exhaust blowdown loss. Now the last one is exhaust blowdown loss. It is seen that at the time of expansion stroke, we have seen in valve timing diagram what we are doing. At the time of expansion stroke, before the end of expansion stroke, what we do, we open our exhaust valve. Why we are doing this? We are doing this so that when there will be a exhaust stroke, the work required to make the exhaust gas go out of the combustion chamber will be reduced. Okay, so we are opening the exhaust valve before the power stroke end. It can be seen in this portion, and because of that, what we are gaining that if we will not if we will not open our exhaust valve before the end of power stroke, during the exhaust stroke, what is there, we have to encounter with 7 bar pressure exhaust gases, and to remove that gases from the combustion chamber, the requirement is more. But once, when we will open the exhaust valve just before the end of expansion stroke, some amount of exhaust gases, which is at the top portion of the combustion chamber, will start moving from the exhaust valve, which reduces the pressure, so that less work is required at the time of expansion stroke. But there is one drawback also. What is the drawback? That if we'll start removing the exhaust gas before the end of power stroke, during the end of power stroke, we will get less work. Okay, so work output will reduce. But if we will not do that, during fourth stroke of the cycle, work input will increase. So when we optimize both the things, we have seen that opening of exhaust stroke just before the top dead center is beneficial if we'll do the optimization. Okay, but it has to be clear in mind that it should not open too early, otherwise it will have more impact on the work loss of expansion stroke, and lot of work will be lost. So it will be the optimization. Again, the optimization come into play. It is not like you will open exhaust stroke much ahead of end of stroke. So exhaust valve must end of exhaust stroke, and the work will be reduced to a great extent. So it has to be optimized. And if you will not open exhaust stroke till the expansion stroke end, what will happen? During the fourth stroke, exhaust stroke, required, the work required to take the exhaust gas from inside the combustion chamber to the outside will be increased, and that will reduce the work output of the cycle. Okay. So what will be the best compromise? It has been seen that if we'll open the exhaust valve 40 to 70 degree before BDC, thereby reducing the cylinder pressure by around 3.5 bar, which will reduce the work required in the fourth stroke. Okay, so overall we have seen that exhaust means opening of exhaust valve just before the end of expansion stroke is beneficial, and it is very much required to improve the efficiency of the cycle. Okay, so this is all for today's class. So we have seen in this class that how a real cycle is different from ideal cycle, and also what are the important factors which make the difference between the ideal and real cycle. So okay, we will meet in next class. Thank you.